Let's apply Kirchhoff's current law and Kirchhoff's voltage law to solve the problem shown on your screen. Let's start with part A. We want to find the current from the power source for the given circuit. In order to apply Ohm's law to find the current from the power source, we need to find the equivalent resistance for the entire circuit. In order to find the equivalent resistance, we should identify what components of the circuit are in series and what components of the circuit are in parallel with one another. To help us do that, we can identify the different nodes on the circuit. Remember the analogy that I used in the last circuit problem that I worked for you all. Driving along the circuit highway, you can follow the lines where there are no circuit components until you reach a circuit component. You do a U-turn and then follow along the line again until you come back to where you started. Identifies a node. We'll call this node 1. Continue that process along until you highlight all the nodes on the circuit. We'll call this node 2, node 3, node 4, and node 5. Once you have your nodes identified, you can use that information to help you understand how current's going to flow through the circuit, where it's going to split. When it splits, it's in parallel, and where it's going to remain the same as it moves through circuit components when it's in series. If we think about current coming from the power source, it's going to pass from node 1 to node 2 through that 25 kilo ohm resistor. There's no separate path for it to take from node 1 to node 2, so that resistor is in series with the power source. Once you are on node 2, going from node 2 to node 5, you have 1 path, 2 paths, 3 paths, 4 paths. So you know eventually you're moving from node 2 to node 5, but you see that there are 4 separate paths for that route. Let's look at each path in more detail. We can move from node 2 to node 5 and pass through just one resistor, the 20 ohm resistor. We can move from node 2 to node 5 and pass through 2 resistors. We have to have a little pit stop here at node 4. But at node 4, there are no 2 separate paths. So we'll go through 5 ohm and 10 ohms. That tells me that because there's no separate path at node 4, the 5 and the 10 are in series with one another. Now I'm moving from node 2 to node 5. In order to move from node 2 to node 5, I have to make a pit stop on node 3. Then node 3, I have 1 path to take to go to node 5. That's telling me that the 6 ohm resistor and the 8 ohm resistor are in parallel with one another, but they're in series with that 30 ohm resistor. So that is a critical observation for you to make, that this 30 ohm resistor is in series with the 6 ohm and the 8 ohm, but the 6 ohm and the 8 ohm are in parallel with one another. So when you're collapsing this circuit, you really need to focus on this parallel section and the series section before addressing any of the other resistors in the circuit. If you were to do the 6, the 8, the 5, the 10, and the 20 all in parallel with one another, you'd be neglecting this 30 ohm resistor. You have to do these 6 and 8 ohms first, because these two are in parallel with each other and then are in series with this 30 ohms. So let's call this segment here segment A and find the equivalent resistance of segment A. Req of A is equal to 1 over 6 ohms plus 1 over 8 ohms. I get 3.429 ohms. Now if I redraw this circuit, I can see that these 2 resistors are in series with one another, and I have to put these in series together and add them together before I can address them being in parallel with any of the other components. Now I can address my new segment here and call this segment B. I can calculate ReqB by adding those 2 resistors together and redraw my circuit. Now, one of the things I have not addressed yet is this 32 ohm resistor. What do you notice about the 32 ohm resistor in our original circuit diagram. Both sides of that resistor are connected to node 5. When you have a resistor where both sides are connected to the same node, what do you know about current? Current is going to flow through the path of least resistance. And so it's going to come through each of the parallel sections that it's coming from, and it's going to pass through the wire, through this connected wire, and never go to this segment here. Because you're giving it a path that has no resistance, it won't ever choose to go to a path that has a resistor. So we can eliminate this 32 ohm completely from our circuit. I'm going to erase it to clean up the circuit to make it easier to look at. Once we erase that 32 ohm resistor, you can more easily see that this 33.429 ohms is in parallel with the 5 and 10 ohm segment and the 20 ohm segment. Now, what do we see about the 5 and 10 ohm segment? These are in series with one another. And we can see that with our nodes. You can see that in order to go from node 2 to node 5, we have to take a stop at node 4, but there's no other path. So we know that 5 ohm and 10 ohms are connected in series. So we can add these up in series with one another. We'll call this segment here C and find REQC. In order to find REQC, we're going to combine them in parallel, but watch what I'm going to do with that 5 and 10 ohm resistor. I'm going to simply add them together in series within my parallel equation. Now I can leave them like this, or I can see that 10 plus 5 is 15, and I can simplify my equation and just write it a little bit easier. Calculate the equivalent resistance for this segment, and I get 6.822 ohms. Now I can redraw my circuit one more time, and I can see that that 25 ohm resistor is in series with all of these resistors that were connected either in series or parallel with one another. And then to find my total equivalent resistance, all I have to do is add those two resistors together because they are in series. And I get a total equivalent resistance of 31.822 ohms. So my equivalent resistance circuit is simply a single resistor with 9 volts and 31.822 ohms. Now, in order to find the current that's leaving the power source, as indicated by the orange arrow on each of my diagrams, I can use that overall equivalent resistance to find that current from the power source. I know using Ohm's law, V equals I times R, and my voltage source is 9 volts. My current is what I'm looking for, and my resistance that I'm using is the equivalent resistance of 31.822 ohms. So my overall current is equal to 0.283 amps. Let's use Kirchhoff's current law to label the current as it splits through the different resistors in the circuit. We know the current that leaves the power source is the total current. So let's call that IT for total. Then we have a current that's going to pass through the 20 ohm resistor. We'll call that I1. And a current that passes from node 2 to node 4 through the 5 ohm and 10 ohm resistors, we'll call that I2. Now, is I2 the same between the 5 and the 10 ohm resistors? Yes, it should be, because those two resistors are in series, and that current has no place to split. So it will be the same as it passes through the 5 and the 10 ohm resistor. Then we have the current that passes through the 6 ohm resistor. We'll call that I3. And we have a current that passes through the 8 ohm resistor. We'll call that I4. Now, as current goes from node 3 to node 5, that I3 and that I4 are going to come back together and give us a new current with those two added together, because I3 and I4 are entering node 3 and then leaving node 3. We'll call that I5. And we already established that there's no current passing through that 32 ohm resistor, so I just exit out on my circuit diagram. Now, this information might help us as we continue to solve the different parts of the problem. Part B asks for the voltage drop across the 20 ohm resistor. How are we going to find the voltage drop across that 20 ohm resistor? If we think about the loop that passes through that resistor, we know that the rises have to balance the drops. So if I address the segment of part B for that 20 ohm resistor, and I say the voltage rise for that loop is equal to 9 volts. We have a voltage drop across the 25 ohm resistor, and then we also have a voltage drop across that 20 ohm resistor. Those are the only resistors that loop passes through. So notice how we leave the 9 volt power source, that's our rise, that's our voltage rise, 9 volts. It passes through the 25 ohm resistor and then the 20 ohm resistor. And so it has to have a voltage drop across the 25, a voltage drop across the 20, and then it completes that loop. And therefore you're only having those 2 voltage drops. Let's look through the loop that passes through the 20 ohm resistor. If we look at loop 1, we see that we have a voltage rise of 9 volts, and then we'll have a voltage drop across the 25 ohm resistor and a voltage drop across that 20 ohm resistor. And those are the only components that go through that loop. So we have a voltage rise equal to 9 volts. We have a voltage drop for the 25 ohm resistor. We don't know its value. And we have a voltage drop for the 20 ohm resistor, and we don't know its value. What we're trying to find is the voltage drop across this 20 ohm resistor. So in order to solve this problem, there's a few ways that you can approach it. One is determine what that I1 value is. However, that will prove to be difficult because we don't know the voltage drop across 20. We don't know the current. We only know that it's 20 ohms in resistance. What we do know is the current that passes through that 25 ohm resistor has to be the current that leaves the power source because it hasn't split yet. It hasn't reached node 2 to where it splits. So maybe we can find the voltage drop here, and knowing that our voltage rise must balance the voltage drops in any closed loop of a circuit, we can determine what the voltage drop across the 20 ohm resistor is by using Kirchhoff's voltage law and subtracting 9 volts from whatever the voltage drop we get across the 25 ohm resistor. So let's do that. We know that the voltage drop across the 25 ohm resistor is equal to current times resistance. And in this case, we're using the total current from the power source because that's the current that passes through the 25 ohm resistor, and the resistance value is 25 ohms. So plugging in those values, we get 0.283 amps times 25 ohms. I get a voltage drop of 7.07 volts for the voltage drop across 25 ohms. Now from here, I know that my rises must balance my drops, so I can say that the voltage drop across the 20 ohm resistor has to be equal to 9 volts minus the voltage drop across the 25 ohm resistor, which is 7.07 volts. So this right here is my voltage rise, and this is the voltage drop across the 25 ohm resistor. So I can determine now that my voltage drop across the 20 ohm resistor has to equal 9 minus 7.07 volts, and I get 1.93 volts. Knowing this information, can we determine the voltage drop for other components within the circuit? To clean it up and make it easier to look at, I'm going to erase this 32 ohm resistor because we know it doesn't have any factor in the circuit because current will not pass through it. That might make it easier for us to look at this circuit. Knowing that the voltage drop across this 20 ohm resistor is 1.93 volts, can you determine the voltage drop across the 5 and 10 ohm resistor? Because the 5 and 10 ohm resistor are in parallel with that 20 ohm resistor, yes, you should know that the voltage drop here across both of these components has to be the same, 1.93 volts. Now, does that also mean that the voltage drop across the 6 ohm and the 8 ohm are 1.93 volts? Take a second and think about that. It's not because of this 30 ohm resistor here. Now, that 30 ohm resistor causes the 6 and the 8 ohm resistor to not be in parallel by themselves with the 5 and the 10 ohm resistor and the 20 ohm resistor. The 6 and the 8 ohm resistor are in parallel with one another and in series with the 30 ohm resistor. And then this whole segment here is in parallel with the 5 and 10 ohm resistor and the 20 ohm resistor. So this whole segment here, the voltage drop, if you were to put your multimeter at this point and at this point and measure across that whole segment here, this whole segment would have a voltage drop of 1.93 volts. But the voltage drop across the 6 ohm by itself and the 8 ohm by themselves are not 1.93 volts. You have to include that 30 ohm resistor in there. So knowing that information, the next question says, what is the voltage drop across that 8 ohm resistor? So in order to find the voltage drop across that 8 ohm resistor, we need to know a little bit more information about the current that passes through it or about the voltage that is divided between the different resistors in that circuit. So looking at part C, let me redraw the circuit to make it a little bit easier for you to see. So these components here are this, and now this segment right here, I'm going to draw it in another way to make it a little bit easier for you to see. This is the same thing as we have drawn above, except it makes it a little easier for you to see how the circuit behaves. Notice I have my 6 and my 8 ohm resistors in parallel with one another, and they're in series with the 30. That is the same thing that we have written above, but now you can see a little bit more easily how the 6 ohm and the 8 ohm are in parallel and then in series with that 30 ohm resistor. So if we're trying to find the voltage drop here, we might need to know what is the voltage drop here, what is the voltage drop here, or maybe the overall voltage drop, or maybe the current that passes through it. So we know that the current that passes through this 30 ohm resistor we have labeled I5. And so the current that's entering that is also I5, except that it splits here, and I3 goes through the 6 ohms, and I4 goes through the 8 ohms. So there is one piece of information on here that we do know. We do know the voltage drop across this entire piece of the circuit. Because this entire section here is in parallel with the 5 ohm and 10 ohm and in parallel with that 20 ohm, it has to have the same voltage drop. So that voltage drop there has to be equal to 1.93 volts. So if we know the total voltage drop across this segment here, we'll call it segment D, then we can calculate the total current that passes through that whole segment, I5. We can say voltage is equal to current times resistance using Ohm's law. We know that the voltage is 1.93 volts. We're trying to find the current, and now we need to find the equivalent resistance for segment D. Now, if I look at what I did earlier, I can see segment D is the same as my segment up here that I identified as segments A and B. So these two right here, when I added them up, I got an equivalent resistance of 33.429 ohms. So I know that my equivalent resistance of segment D is 33.429 ohms. So I can find the current here through that whole segment of the resistor, segment D, by using Ohm's law with the voltage drop across that segment, that entire segment, in the equivalent resistance. And I get 0.0577 amps. So I know that I5 is 0.577 amps. Knowing I5 is 0.577 amps, I know that that value passes through that 30 ohm resistor, so I can use that information to find the voltage drop across the 30 ohm resistor. The voltage drop across the 30 ohm resistor is the current that passes through it times its resistance value. So I have I5, which is 0.0577 amps times 30 ohms, and I get 1.731 volts. Now that's the voltage drop here across that 30 ohm resistor. Now how can I find the voltage drop across the 8 ohm resistor? That's what I'm trying to find. Now I know the voltage drop across the 8 ohm resistor and the 6 ohm resistor have to be the same value because they're in parallel with one another. And so I know if I'm looking at my loop here, my voltage rise is the value of voltage at this point right here because I'm only looking at this segment of the circuit. And I can see my loop here. My rise has to balance my drops. So my rise is 1.93. That's what I'm starting with at this point of the resistor. I'm going to drop a little bit over the 8 ohms, and I'm going to drop the remainder over that 30 ohms. My second loop that I have here, I can go from my rise of 9.3 volts through the 6 ohm resistor and then through that 30 ohm resistor. That 30 ohm resistor, we know its voltage drop value is 1.731 volts. And so it's always going to have that 1.731 volts. So if it's always 1.731 volts, then the voltage drop across that 8 ohm resistor and that 6 ohm resistor has to be the same. That makes sense because they're in parallel, and according to Kirchhoff's voltage law, they would have to be the same value. So I can use KVL to determine the voltage drop across the 8 ohm resistor is equal to the rise, which is 1.93 volts. That's the voltage drop that's the total voltage drop that it has in that segment of the circuit, minus the drop across the 30 ohm resistor, which is 1.731 volts. And I get a value of 0.199 volts. So my voltage drop across the 8 ohm resistor is 0.199 volts. For notation's sake, I can also say that that's the voltage drop across the 6 ohm resistor. Now the last thing that I'm asked for in this circuit is part D, and that is the power dissipated by the 30 ohm resistor. After doing all of this work, we've applied Kirchhoff's voltage law and Kirchhoff's current law to all the different parts of the circuit, and we know a lot of information about that 30 ohm resistor. We know the current at the 30 ohm resistor is I5, which equals 0.0577 amps. We also know the resistance value at the 30 ohm resistor is 30 ohms. That was given to us in the problem. And we also know the voltage drop across the 30 ohm resistor is 1.731 volts. So there's a few paths we can take by calculating the power at the 30 ohm resistor. You can use any one of the equations that we've used in class. And so I'm going to choose the easiest one of just doing I times V. So I'm going to have 0.0577 amps times 1.731 volts. And I get a power of 0.0999 watts. Now, this was a very involved problem. There were a lot of things that you had to observe correctly in order to work the problem. One of the main observations you had to realize was this 30 ohm resistor and how it affected the 6 and the 8 ohm resistors in the circuit. Additionally, you had to realize that that 32 ohm resistor had no effect on the circuit, and we could just eliminate it from any of our calculations. Doing circuits is like a puzzle. Now that you have Kirchhoff's current law, Kirchhoff's voltage law, the power equation, and Ohm's law, you have all the tools in order to sort the puzzle and find the different pieces and solve for every part of the circuit that you could be asked about. Just pay attention to your nodes, how current flows, and how voltage behaves throughout the circuit.